everyone and welcome. In this video I'm going to cover 5 different concepts, in which first we'll start by the definition of monomial functions with one variable. After that we'll extend the definition and we'll define polynomial functions as addition of monomials. Then we'll learn that the domain of definition of polynomials is simply the real set, and after that we'll learn how to compute limits of polynomials at a point, then at plus and minus infinity. So first of all, I'll start with the definition of monomials with one variable, in which I can say a monomial function is a function in the form f of m of x equal to a x to the power n, in which a is a non-zero real number, x is a variable, and n is a whole number. Of course, you can go back and check my previous video so you can learn the difference between real numbers and whole numbers. As an example of monomial, I can take m of x equal 3x power 7. In this particular function, I can say that 3 is the coefficient of x power 7 and 7 is the power or the degree of the monomial. So basically, I can tell that the degree of m of x here is simply 7. Other example, like m of x equal to 12x power 13 as an example. Here, in this case, the degree of m of x is equal to 13. So as you see, the degree of the monomial function is defined by the power. And now, after monomial functions, we are ready to extend this definition and explain the definition of polynomials, in which I can say a polynomial is given as the addition of monomials with different degrees. So I can say it as m1 of x plus m2 of x plus, let's say, mn of x. As an example, I can take p of x to be 7x power 2 plus 3x plus 1. This one is a polynomial function, and it's clear that it's addition of 3 monomials, 7x power 2, 3x plus 1. But the degree of polynomials is a bit different than the degree of monomials, in which we choose the degree based on the highest power in the equation or in the function. And here the highest power is 2. That's why we say that the degree of this polynomial is simply 2. Other example, like I can take p of x equal negative 13x power 2 plus 7x power 3 minus 11 plus 12x power 7. So also here, as you see, this polynomial is given as addition of monomials with different powers. And here, since 7 is the highest power in this polynomial, so I can tell that the degree of this polynomial is simply equal to 7. Now, concerning the domain of definition of polynomials and monomials, we'll see that the domain of definition is simply the real set, in which this type of function is defined over all real numbers, and we don't have any problem with any number. Now we can move to the fourth point, in which we are going to learn how to find the limit of polynomial at a point. First of all, I'll teach you how to find the image of a polynomial. To find the image of polynomial, let's say, for example, let me use an example. Let's say if you have p of x is equal to x plus 1, and let's say I want to find the image of this polynomial at 2, is simply finding the image is to replace x by 2. In example here, it will be 2 multiplied by 2 plus 1. So here the image of p of x at x equal 2 is simply 5. Similarly, let's say if I want to find p of 3, I'll say that 2 times 3 plus 1, so this will give 6 plus 1, so it will be 7. And here I have something very important that relates the image of a polynomial with its limit, in which I can say limit as x tends to a for a polynomial p of x is simply given as p of a, which means that if I want to find the limit at any particular point, all what you need to do is to replace this point in the polynomial. And I can take an example. Let's say p of x equal 3x power 2 plus 5x minus 1, and suppose that I want to find the limit as x tends to 2 for p of x. So simply here I can say that this limit is equal to p of 2, in which I can go and replace every x by 2. So I'll get 3 times 2 power 2 plus 5 times 2 minus 1. So I'll get 12 plus 10 minus 1, 22 minus 1, so this will give 21. And so as you see, finding the limit as x tends to a for p of x is similar to find the image at a at x equal to a. Later on, we also will see the reason why this statement is correct, because later on we shall define continuous, or the definition of continuous function, and we'll learn that polynomials are continuous over the real set. And now finally I'm going to move to the last point, in which we are going to learn how to find the limit of polynomial at infinity. But before I start with this point, I would like to remind you by some facts about infinity, in which we know that if we add two infinities, the result will be plus infinity. So plus infinity is plus infinity. And we know that, for example, if I put any power for plus infinity, this will go also to plus infinity. If I multiply plus infinity by negative, this will go to negative infinity. Similarly, if I have negative infinity, this will go to negative infinity. But if I have negative infinity with a power, here I need to distinguish between two cases. If the power is even, then this will give plus infinity, so same as real numbers. While if the power is odd, this will go to negative infinity. Example, negative infinity power 3, this will go to negative infinity because simply 3 is odd. And negative infinity power 4, this will go to plus infinity because 4 is an even power. In addition to the above, while finding the limits, one can face a very important case or scenario in which when we have plus infinity minus infinity. This case we need to pay attention, or this is different and it doesn't equal to 0 in general. We can't say that this is 0. And this case is known as indeterminate case or IDF case. And here, this needs from us to find a different method. And the thing is, you will see that there is high probability while finding the limit or computing the limit of polynomials to face this case, in which we can't say and we can decide that the limit is 0 here. To explain this more and to give you the solution, I'm going to continue with a particular example. So as an example, let's say I have the polynomial function p of x equal 3x power 2 minus x plus 1. And let's say that we need to find the limit as x tends to plus infinity. So first of all, I'll say limit as x tends to plus infinity for p of x. And I will go and replace every x by plus infinity. So 3 into plus infinity power 2 minus infinity plus 1. Plus infinity power 2, this will give a plus infinity. 3 times plus infinity, this will give plus infinity, minus infinity, and constant doesn't matter. So here I'll get plus infinity minus infinity. And as I told you, this is an IDF case in which we can't say that this is equal to 0. So for this reason, we need to find another method. Whenever we face an IDF case, we need to find another method. But what shall we do in this case or in this situation? In this situation, all what you need to do is to go back to the polynomial and choose the term with the highest power, or the term that have the degree. And in my case here, 3x power 2 is the term with the highest degree. Then simply this limit will behave as the limit of 3x power 2. So as you see, I'm ignoring all the terms that having power that having power different than power 2. So this will be equal simply to 3 into plus infinity power 2, so which is equal to infinity, which means that limit as x tends to plus infinity for p of x is equal to plus infinity. Similarly, if I want to compute the opposite the limit at opposite infinity, I can say limit as x tends to negative infinity for p of x is equal to limit as x tends to negative infinity for 3x power 2, which tends to 3 into negative infinity power 2, and this will go to infinity. And you don't need to worry, because you can always do this. And you can whenever you want to find the compute at infinity, the limit at infinity for any polynomial, all what you need to do is to pick the term with the highest power or with the degree and find the limit of this term. Let me do one more example so I can make sure that the idea is clear. So let's say p of x equal 17x power 2 minus 7x power 4 plus 12x minus 13. So if I want to find the limit as x tends to plus infinity for p of x here, all what I need to do is to go to the polynomial function and choose the term with the highest degree. And here we have to pay attention for the sign. So this will be same as limit as x tends to plus infinity for negative 7x, or negative 7 multiplied by plus infinity power 4, and this will go to negative 7 times plus infinity, and this will go to negative infinity. And so with this, we covered 5 different points in which we defined first monomial functions, and we said that monomial functions are given as ax to the power n, in which a is a non-zero real number and n is a whole number. Then we defined polynomial functions as addition of monomials with different degrees. After that, we learned that the domain of definition of both monomials and polynomials is the negative infinity to plus infinity, or the real set. So this kind of function is defined over the whole real set. Then also we learned that limit as x tends to a for p of x is simply equal to the image at a, so it's equal to p of a. And finally, we learned how to compute the limit as x tends to plus or minus infinity for p of x, and we learned how to avoid the case plus infinity minus infinity. And of course, remember that plus infinity minus infinity doesn't mean that this or doesn't go to zero in general.